Thank you. So yes, this is probably slightly different content from many of the other talks at this meeting, but physical reservoir computers are definitely embodied and their morphologies are important. So please bear with me as I go through this. First of all, I'm going to just quickly go through what a reservoir computer is for people who might not know this. Sorry, I've got the wrong view in front of me. Too many different screens. Yes, so I'm just going to talk about what a reservoir computer is. So the model of a reservoir computer, and I'm just going to be talking about echo state networks today, is a recurrent neural network. And so that's the idea that this might be related somehow to neuromorphic computing. And it's a random recurrent neural network at the center of this system. And we feed inputs in through a weight matrix, W in. The random recurrent neural network processes this, and it's got random connections. And then the output is read through an output weight matrix. So it looks like a normal neural network in some sense. And here's the equations for people who prefer equations to pictures. We have a state vector x, and this is updated in discrete time steps through the weight matrix, incorporating the inputs, and then fed through some nonlinear thresholding function, which is usually the tan h or something like that. And so what we have here is an instance of an open dynamical system. And the fact that it's can be thought of as an open dynamical system becomes important when we think about physical reservoirs. And then the output is read out through the output weight matrix, as I said. Now, what's important about reservoir computing is that both the input weight matrix and the internal weight matrix are, in the model, chosen randomly. Not only are they chosen randomly, they are fixed. They are given. The only part of the system that is trained is the output weight matrix. And this can be trained through a simple one-step process. You don't need to have a long iterative backpropagation process. And so what you can have is exactly the same reservoir and then use different output weights for different tasks. So in other words, you can have the system and you can just look at it in different ways to solve different problems. So in some sense, the reservoir can be thought of as a general purpose computer and the output weights as the program. It might seem a bit strange what's going on here, but what's going on is that the dynamics, the nonlinear dynamics of the reservoir are taking the input signal and projecting it into a very high dimensional space. And if that all works well, you can then look at the different parts of this high dimensional space through this linear output weight matrix in order to solve your problem. Now, remember I said that the important thing was that the weights inside this dynamical reservoir are fixed and that it looks like an open dynamical system. And so what we can do is we can replace the interior with a different dynamical system. And in fact, we can replace it with a physical piece of stuff that has the right dynamics. And this is now a physical reservoir computer or a hardware reservoir. And so a key property of that is because this is a black box, we can the interior is a black box and we train the external weights only, we can replace it with any material that has suitable properties, a suitable substrate material. So it has to have a rich nonlinear dynamic so that it acts as an open nonlinear dynamical system. It has to be excitable by an input stimulus. In other words, you have to be able to feed input into it. And you have to be able to read an output state. So you have to be able to observe it somehow in order to get the outputs from it and put those outputs through the trained weight matrix. It's also useful to be able to have a system that's where a single instance is configurable into somehow different reservoirs. And the idea here is that although I said that a single reservoir with its random weights can be programmed for different tasks, actually slightly different reservoirs are slightly better at certain tasks. So if you can configure a reservoir somehow, then it can be adapted to perform better on different tasks. And I'll come on to how that is useful later. In some sense, you can think of this configuration as changes to its morphology, but it's not changes. These changes are in a different morphological space from sort of plain 3D space, because when you look at these different configurations, it hasn't changed the shape, but it might have changed the internal structure in such a way that the dynamics have been modified slightly. So some people say, are these materials really reservoirs? They're certainly not recurrent neural networks in the sense they don't have neurons in them. They don't have connections between the neurons. They are a different form of dynamical system. But in order for them to be used as reservoirs, the material doesn't have to emulate the computational model, the recurrent neural network model, on a fine-grained level. As long as the dynamics are sufficiently rich to be able to separate the input signals into this high-dimensional nonlinear space. And as long as the training algorithm works, then we can consider these things to be a physical implementation of the reservoir computer abstract model, even if there is not a neuron or even an analog of a neuron in sight. After all, we don't say that simulations of artificial neural networks inside ordinary PCs clearly aren't neural networks because they don't have neurons. In the same way, these materials, they don't have neurons, but they can be reservoir computers. But what is happening is that what we're doing is directly exploiting the natural nonlinear dynamics of the material itself. So, okay, how do we go about designing these things? The usual thing is to say, I give you a lump of goo and ask you to build a reservoir computer out of it. How are you going to go about designing these particular systems? So first of all, it's useful to be able to tell when a system is actually computing, when a physical system is computing, rather than just doing its thing somehow, rather than just sitting there as a physical system. What's the difference between it computing and it just being a physical system? So here's the approach that we use to determine when a physical system is computing. So we start off in the abstract domain, and we have some model of our problem, and we perform some abstract computation to get the after state or the answer to our problem. And that computation is done within the context of a computational model. And in classical computing, that computational model is the Turing or von Neumann or whatever kind of classical model. Here, that computational model is that of reservoir computing, so the echo state network, recurrent neural network model. So this is all in the abstract. Well, what we have to do is we have to instantiate the model in some physical device, be it a classical computer or some physical material for our reservoir computer. And then that physical system evolves over time to give an after state. And we then have to read out from that after state or decode the output from that into an answer. You notice here we've got two answers. We've got one answer that came from our abstract computation, and we've got another answer that comes from our physical device. And what we would like is that those two answers be the same, or at least what we say is sufficiently the same, because particularly if you've got an analog system, they might have small errors and so on, but they need to be sufficiently close. And then we say that if this square here sufficiently commutes, then we can say that this device is computing. So notice that this requires us to have an abstract idea of what the computation should be. We also need a physical device that's doing its thing, but then we need these extra steps of the instantiation and the decoding or the representation of the output. And we call this rather grandly AR theory, abstraction representation theory. But what we mean is this sufficiently commuting square. Theoretical computer science tends to focus on the top level and just assume that everything happens by magic in some abstract realm. But a lot of physical unconventional computing focuses on the bottom level of making devices do exciting and interesting things. But these two levels actually need to be linked together for this to be some form of computation. So this is the definition of when a physical system computes that we use. Here's an abstraction of that square with the four sides indicated the important parts. The AR theory was developed in order to define when or if a physical system computes, in order to particularly to critique some of the more bizarre suggestions of unconventional computing and when things may be computing and not. But having got this definition, we can now use it to help us design a novel computer. We have to design each of these four arms such that the total square sufficiently commutes, and then we have the novel computer. And this design process can often start either from a material first or a model first approach. A material first approach is I've got a material and then I've got to find the other three arms such that I can say that it's computing. Here we're starting with a model first approach, is to say we've got the reservoir computing model, we've got the top arm, we know how we think this thing should be computing, can we therefore make it compute? So we need a physical material that supports that particular computational model. So here we've got the echo state network reservoir computer model at the top. And then what we have to do is design the other three arms so that everything links up together. So this is an iterative process. We can't do it in a sequential manner because changing one of the arms changes the requirements of the other arms. So for example, I said you have to be able to instantiate the problem, the program, the data into the physical material. You have to be able to put something into it. So how do you do that? What are the physical inputs into the system? Are you going to use voltages or currents, photons? One of the systems we're using at the moment, we use rotating magnetic fields to input the information. And then you have to decode the output. You have to look at the state and work out how to measure parts of the state from it. So again, it could be similarly voltage and currents and so on, but there's no reason why the output modality and the input modality need to be the same, which is quite interesting because that means that you can use one of these reservoir computers to do signal transduction as well, because you can have a different input and output modality. But rather than just doing a straight translation, it can do some computation on it at the same time. So a very smart filter or something. And that's one of the interesting applications of these systems, is maybe as smart edge computers, so that you can incorporate your sensor, your computing and your signal transduction all in one device in one go. And one of the things we're thinking here is analogues of things like the interesting processing that goes on in sensors like the ears and eyes and those kinds of things. There's a second half to the instantiation and decoding, is the representation, the abstract representation of programs, data and output, and that can also change what's needed. And then a design of the physical material that can take these inputs, has the right dynamics, and can have the outputs decoded. And then this all has to be assembled in such a way that the square sufficiently commutes, and then, hey presto, you've got a physical reservoir computer. And this is the way we go about designing these things. And then we end up with a blob of goo on the bench that is now a physical reservoir computer, but we also want to know how good this is. We've built the reservoir, but how good is this reservoir at being a computer? Is it a little tiny computer that can only do a very small amount, or is it quite a big, powerful one? And of course, this question is representation dependent as well. Now, very often, the solution to this problem people take is to use benchmark tasks to evaluate how well the computer performs. But of course, which benchmarks should you use? Why should you choose those benchmarks? How does those answers generalize to other tasks? That's all very contentious, and very often benchmarks are cherry-picked to show that your computer is better than somebody else's computer. So what we do is instead we use generic computational capacity measures of the device. We happen to have chosen these three. Kernel quality, I said the way that the reservoir computer works is to project the input into a high dimensional space, and kernel quality measures how well it can do that. But also generalization, we don't want it to overfit noise and so on. So if you've got similar inputs that differ only by a little bit of noise, we want that to give the same output. And so that's a different measure of generalization capacity. And in some sense, how large a reservoir it is, how much memory has it got, and so what is its memory capacity. And as I said, other computational capacity measures are available, and you can use those as you like, but these are the three that we are currently using. We have a technique called CHARC, which stands for something that I can't remember. The RC is reservoir computing, and there's something about characterization, but I can't actually remember what it stands for, which we use to characterize these things. And the first step is actually characterizing the computational model itself. What is the computational capacity of the computational model? So we build a simulation, a direct simulation of the computational model. And we use a technique called novelty search, which is a kind of evolutionary algorithm that uses novelty as its fitness rather than some specific fitness, an optimization technique, to explore the space. So it's a purely exploration with no exploitation algorithm. And we use that to find out how much of this computational capacity space the actual echo state network itself can inhabit by fiddling around with the internal weights and various other parameters and so on. What echo state networks can we find? And we use this as a baseline measure. And we can then use this to find regions in this space where a particular task, be it a benchmark task or a real task, performs particularly well, what particular reservoir forms well. So some tasks require different properties from other tasks. So here's this conceptually, the gray box is the space, the computational capacity space. The cloud represents how much of it can be filled by echo state networks, and the stars represent places in this space where particular tasks are performed particularly well. And then we characterize the actual material. And again, we use novelty search in exactly the same way to discover its computational capacity. And then we can use the mapping established from characterizing the model to find suitable material instances, suitable material morphologies, I might say, for those different tasks. So here we've got maybe three different materials. Material one has a large computational capacity, but it turns out that because of where it sits in the space, it can't perform the blue task. Material two has a somewhat smaller computational capacity, but in fact, it manages to perform both of those tasks quite well. And then material three has a very small computational capacity, but sufficient to perform the blue task, even if it can't perform the yellow task. And notice here that we only have to evaluate where the tasks fit in the space once, so we don't need to run the benchmarks on all the different materials, we only need to evaluate them. So just to summarize and conclude, the physical properties of materials can be directly exploited to perform computations by exploiting their nonlinear dynamics. Examples, reservoirs. The AR theory lets us know when these physical systems are computing, and it also allows us a way of designing novel computers that exploit these materials. And then the Chark approach allows us to characterize the computational capacity of these, so we can design the materials and then figure out how good they are as reservoir computers. So thank you.